Right now, as you are watching this, the two most powerful global weather models on Earth, the European ECMWF and the American GFS, are showing the same signal for the same reason at the same time. And the researchers at the Center for Western Weather and Water Extremes at Scripps Institution of Oceanography have just issued the earliest strong atmospheric river forecast the West Coast has received in the modern forecasting era. On August 14, 2026, both models converged on a scenario that no West Coast forecaster expects to see this early in the season. A distinct plume of concentrated water vapor, more than 1,500 kilometers long, drawing its moisture from the deep tropics near Hawaii and organized into the classic filament shape that meteorologists recognize on satellite imagery as an atmospheric river, is projected to form in the eastern Pacific over the coming week and make landfall on the Pacific Northwest and Northern California coast in early September. The projected integrated water vapor transport places this event in the AR3 to AR4 category on the CW3E's 5 level intensity scale, a strong to extreme atmospheric river. That would be a serious event in November. It would be a significant event in October. Arriving in the first week of September, when Pacific Ocean temperatures are near their annual peak and the atmospheric machinery that normally organizes these storms is only just beginning to spin up, it is essentially unprecedented for the modern satellite era. The West Coast atmospheric river season does not usually begin in earnest until late October or November. The first AR4 of a season historically arrives in December or January, not September. This forecast is arriving weeks, in some measurements, months ahead of the pattern's normal calendar. And here's why every water manager, emergency planner, and wildfire operations chief on the West Coast is paying immediate attention. This is not one strong storm arriving alone. What the models are showing is the entire storm track pattern, reorganizing weeks ahead of schedule, the Aleutian low deepening early, the Pacific jet stream extending eastward earlier than typical, and the Madden-Julian oscillation, a slow-moving pulse of tropical rainfall that circles the equator every 30 to 60 days, entering a phase that historically strengthens Pacific storm generation, combined with the La Niña base state we covered in our recent weather shift video and with Pacific sea surface temperature, anomalies that remain elevated from the summer. The setup that normally takes 6 to 8 weeks to build in September and October appears to be building in 3. Today we break down what an atmospheric river actually is at the physical level, and why one pattern of Pacific moisture can dump more water in 3 days than most cities receive in 3 months. Why faster than expected matters enormously for the systems that plan around this season, the two most instructive West Coast atmospheric river events of the past decade, one where preparation held infrastructure together against a system that came within minutes of catastrophic failure, and one where a warning was issued and 23 people died anyway. And what a West Coast that is about to be tested weeks before it expected to be needs to do this week. No guessing, no dramatizing, just the meteorology, the record, and the real stakes. Drop a comment right now. Are you in the Pacific Northwest, in California, or anywhere on the West Coast? Do you remember an atmospheric river event, the January 2023 sequence that turned California drought to flood in weeks? The 2017 storms that nearly destroyed Oroville Dam, the 2018 storm that erased Montecito. Tell me your city and what you remember. And for everyone else, had you ever heard the phrase atmospheric river before it started showing up in headlines? Because it is one of the most consequential weather phenomena on Earth, it has been named and studied for decades, and it is only in the last few years that the general public began learning what it means. Subscribe right now if you want every atmospheric river forecast, CW3E bulletin, and major West Coast weather development covered, as it happens, completely free. A thumbs up puts this in front of the tens of millions of people whose water, whose highways, and whose safety are about to be shaped by the pattern this video describes. Let us go for 6,000 likes. Now let us get into what an atmospheric river actually is, because most viewers have never had this explained properly. Atmospheric rivers are narrow, elongated corridors of intense water vapor transport in the lower atmosphere. On a satellite water vapor loop, they appear as long ribbons of moisture, typically hundreds of kilometers wide and thousands of kilometers long, streaming from the tropical oceans toward the mid-latitudes. The largest atmospheric rivers on Earth transport water vapor at rates comparable to the total discharge of every river system draining into the world's oceans combined. when one of these vapor rivers makes landfall against a mountain range. The coastal ranges in Sierra Nevada of California, the Cascades of Oregon and Washington. The terrain forces the moist air upward, cools it, and condenses out the water at extraordinary rates. This is called orographic lift, and it is why a single atmospheric river event can drop 20, 30, or even 60 centimeters of rain in 24 to 72 hours across a narrow band of coastline. The Pacific version of this phenomenon is often called the Pineapple Express, when its moisture source can be traced back to the subtropical Pacific near Hawaii, hence the name. It is not an exotic weather curiosity. Atmospheric rivers deliver 30 to 50% of the total annual precipitation to the entire U.S. West Coast. The California snowpack, the Columbia River flow, the reservoirs that supply Seattle and Los Angeles alike, all of these depend fundamentally on the atmospheric rivers that arrive each winter. A dry AR season is a drought, a wet AR season is a flood year, and the sequence, intensity, and timing of the ARs across a season is what determines whether the winter is manageable, catastrophic, or salvational, depending on the region and the year. The CW3E scale from AR1 to AR5 captures both intensity and duration. An AR1 is weak and primarily beneficial. It fills reservoirs, adds to snowpack, and passes without significant flood risk. An AR3 is strong, beneficial for water supply, but with genuine flood risk, particularly on saturated ground. An AR5 is exceptional and hazardous, the atmospheric river equivalent of a Category 5 hurricane in terms of raw water delivery to a landscape. The models this week are showing an event that could reach AR4 in early September, when the West Coast's reservoirs, dams, and drainage systems are configured for late summer conditions rather than winter storm seasons. Now, why does faster than expected matter so much? Because West Coast water management is a calendar-driven system as much as it is a weather-driven one. Reservoir operators run their systems on a seasonal rhythm, drawing reservoirs down through the summer for water supply and hydropower, then transitioning to flood control operations in the autumn as the storm season approaches, and rebuilding reservoir storage through the winter and spring. The transition from summer drawdown mode to winter flood control mode happens according to schedules that are locked in weeks and months in advance, with staff shifts, spillway inspections, and coordinated releases across dam systems, tuned to the historical calendar of when the storms arrive. An AR4, arriving in early September, finds the West Coast's largest reservoirs still in summer supply configuration, designed to be as full as safely possible for water availability, not as empty as needed to absorb a major flood. It finds burn scars from a summer that has been running elevated wildfire activity, ground where vegetation has been destroyed, soils have been hydrophobically altered by fire, and the risk of debris flows from any significant rainfall is dramatically higher than on unburned ground. It finds emergency management staff who are still cycling out of wildfire deployment posture and have not yet fully repositioned for winter storm response. And it finds highway maintenance crews who are performing summer paving and repair projects on the very roads that the storm will pound. Every one of those systems is designed to handle atmospheric rivers, but designed to handle them starting in October and November. Faster than expected means the calendar's assumptions are wrong. It means the design basis for readiness needs to be advanced by weeks. It means people, agencies, and infrastructure that would have been ready in November are being tested in early September instead. Now let us talk about what the tests look like. Because in the past decade, the West Coast has produced the two clearest examples in modern American weather history of what preparation does and does not do when an atmospheric river makes landfall. In February 2017, at the peak of a very wet winter that had erased California's 5-year drought, a series of atmospheric rivers slammed into the northern Sierra Nevada. The Feather River filled Lake Oroville, America's tallest dam and one of California's largest reservoirs, faster than the dam's main spillway could safely release water. On February 7th, engineers discovered a massive hole in the main spillway concrete during a release event, and the spillway began disintegrating catastrophically under continued flow. As the reservoir approached the level of the emergency spillway, an unlined earthen slope that had never been used in the March dam's 49-year history, engineers made the terrible call to use it, only to watch it begin eroding immediately toward a scenario where a total failure of the emergency spillway could have released a wall of water down the Feather River toward the cities of Oroville, Marysville, and Yuba City. On February 12, 2017, evacuation orders went out for approximately 188,000 people downstream of the dam. They left. Traffic on Highway 70 became a crawl of taillights heading south. Engineers threw everything they had at stabilizing the emergency spillway while draining Oroville as fast as the wrecked main spillway allowed. And the dam held. The emergency spillway did not fail. Repairs began within days, and over the following 2 years, the Oroville spillway was rebuilt to modern standards. The total death toll from the Oroville crisis, 0. From a scenario in which a fully instrumented, fully modeled dam nearly experienced catastrophic failure in the middle of an atmospheric river event, 188,000 people were evacuated and every single one of them returned home. The system combining engineering monitoring, decisive institutional action, and public compliance with an evacuation many later called unnecessary worked exactly as it was supposed to work. Now look at January 9, 2018. 6 weeks earlier, the Thomas Fire, then the largest wildfire in California history, had burned 114,000 hectares of chaparral forest in Santa Barbara and Ventura counties, including the mountain slopes directly above the community of Montecito. On January 8th, an atmospheric river approached the Southern California coast, projected to deliver intense rainfall directly over the burn scar. Santa Barbara County issued evacuation warnings for the area immediately below the burned slopes. The warnings were voluntary for a portion of the affected area because previous rain events on the burn scar had not produced catastrophic debris flows and because officials were cautious about triggering evacuation fatigue after the extended Thomas Fire evacuations. Some residents evacuated, many did not. At approximately 3:30 a.m. on January 9th, the rain hit the burn scar. Fire-altered soils, unable to absorb the rainfall, released water rapidly downslope. That water gathered in the drainage channels above Montecito, picked up rocks and boulders, gathered mud and debris, and became a debris flow, a fast-moving slurry of water, mud, and rock that surged out of the canyons above town with the consistency of wet concrete and the speed of a highway vehicle. 23 people died as the debris flows tore through Montecito neighborhoods that had not been under mandatory evacuation. Homes were destroyed, Highway 101 was buried, and post-event analyses reached the difficult and honest conclusion. The meteorological forecast had been correct. The atmospheric river had done exactly what was expected, but the pairing of that forecast with the specific hazard on the ground, a burn scar that had crossed a threshold where any significant AR event would produce a catastrophic debris flow, had not translated into mandatory evacuations for the specific streets where 23 people would die. Oroville 2017 and Montecito 2018 are the two poles of atmospheric river response. Oroville shows what works when engineering, institutions, and public compliance align against a fully anticipated hazard. Montecito shows what happens when a correct forecast meets a hazard threshold that the response framework did not fully appreciate, and when the difference between voluntary and mandatory evacuation is measured in the willingness of specific families to leave in the middle of the night on the basis of a warning that could still, in principle, be wrong. The early September 2026 atmospheric river will land on a west coast whose calendar preparation assumes it is a month too early for this pattern. It will land on burn scars from a summer that has been running elevated fire activity. It will land on reservoirs configured for summer supply rather than winter flood control. It will land in the middle of school year startup, when Highway 101 and Interstate 5 traffic reflects new commuter patterns that the emergency response coordination is not yet recalibrated for. Every one of those factors makes the Montecito category of concern a correct forecast landing on ground in communities that are not fully positioned more consequential than it would be in the middle of the season. Let us be direct about the practical message, because information without action is just anxiety. If you live in the Pacific Northwest, Western Oregon, Western Washington, coastal British Columbia, the September AR event is likely to deliver very heavy rainfall, potential rapid rises in river levels, and elevated landslide risk on saturated slopes. Check the NWS river forecasts for your local river system in the days ahead. Do not underestimate the storm because it is early. AR4 in September behaves like AR4 in November. With the mud, does not know the date. If you live in California below any 2025 or 2026 burn scar, this is the specific week to review your county's post-fire debris flow warnings. Voluntary versus mandatory evacuation distinctions have killed people. If your area is under any evacuation warning during the AR event, believe. Montecito is the reason the phrase evacuation fatigue is no longer used casually by any responsible emergency manager on the West Coast. If you manage water, infrastructure, agricultural operations dependent on flood management, or emergency response in any West Coast jurisdiction, the September event is the wake-up call for the season, not a preview. Any assumption that November represents your effective readiness deadline needs to be re-examined this week. Pre-positioning of resources, spillway inspections, and staff readiness plans built for later in the calendar need to be advanced. If you live anywhere on the West Coast, enable wireless emergency alerts on your phone, verify your county's evacuation notification system enrollment, and remember that atmospheric river events can cause rapid road closures, particularly on mountain passes and coastal highways. Do not drive through flooded roadways. The single most common cause of death in West Coast AR events is people attempting to cross water on roads that appear passable but are not. Final thought? The Pacific Ocean is a warm expanse that most West Coast residents look at daily and rarely think about as a machinery. But it is a machinery, an enormous thermal, wind, and moisture engine that spins up its winter storm, generating configuration each autumn on a schedule that is held roughly stable for the entire modern instrumental record. This year, the models are showing that machinery spinning up weeks early, driven by a Pacific that is warmer than average, a jet stream that is repositioning ahead of schedule, and a Madden-Julian oscillation that is arriving at exactly the right phase to reinforce Pacific storm production. The pattern is not new. What is new is its timing. Faster than expected is not by itself a disaster. It is a change in the calendar of readiness. The West Coast has spent decades building the reservoir operations, emergency response systems, evacuation frameworks, and public communication infrastructure to handle atmospheric rivers when they arrive on the historical schedule. Advancing that schedule by a month is a test the system was not asked to run this year. Whether it passes will depend on whether the water managers, the county emergency managers, and the residents in the burn scar shadow all take the September event as seriously as they would take the same event in November. Oroville held because everyone acted. Montecito lost 23 people because a hazard threshold was not fully recognized in time. The forecast for early September is real, it is early, and it is honest. What happens next is the choice of the systems and people the storm is about to reach. We will track every model update, every CW3E bulletin, and every West Coast weather development from the September event and the atmospheric river season that appears to be arriving alongside it. Subscribe so you do not miss it. And leave that comment, your city, your relationship with atmospheric rivers, and whether the September event is on your radar yet, because the calendar of preparation is not going to move itself. 6,000 likes. Let us go.